Good day to you. I'm John Kolak, the president of Praxis Corporation, and I'll be your instructor today for a webinar entitled The NFPA 70E, The Importance of Risk Assessment in Electrical Safety Programs. Now, we'll be talking about risk assessment both from the perspective of the NFPA 70E itself, but I'd also like to introduce some important hazard assessment or risk assessment concepts that are included in something called system safety engineering. And system safety is foundational to safety, and there's a couple of tools that I would like to introduce to you today, which I believe will be very helpful to you and your organization as you assess risk and determine appropriate hazard controls. Now, my background in safety that's relevant for this discussion is that I have a master's degree in occupational safety, and I'm a certified safety professional, and I've been in the industry for about 40 years. Let's go ahead and go to the next slide. Now, the NFPA 70E talks about risk assessment in Article 110.1, and there it suggests that a risk assessment is required anytime there's an exposure to an electrical hazard. And we're going to define an electrical hazard from the shock perspective as being either 50 volts AC or 100 volts DC. And we're going to talk about arc flash hazards in the context that a hazard would be defined as 1.2 calories of incident energy or more. Now, the process for risk assessment has to include how we are asking employees to do a risk assessment. Now, risk assessment exists in any organization on at least two levels. The formal risk assessment, as we see, is a management function, and that is usually done by safety professionals and engineers, and that's included in things like your job safety analysis or your job briefing discussion forms. But there's also a need to do an ad hoc risk assessment on the job, and this can happen anytime there's something in a non-standard condition, like, for example, an overcurrent device or a switch that malfunctions. In those situations, the qualified electrical workers are going to be required to come up with an equivalent system, and risk assessment is integral to that process. Let's go ahead and go to the next slide. There are a few important system safety concepts that we need to talk about on the front end of the presentation, and we'll integrate them into the risk assessment process as we progress. The first one is called life cycle management, which is also known as cradle to grave. Life cycle management recognizes that the hazards associated with any system change depending upon where one is in the system life cycle. Now, the system life cycle exists both for a piece of machinery, and it also exists for the human machine as well. So, for example, if we're talking about an electrical motor, the first time we energize the motor, when it's brand new, it has a higher than average failure rate when you first energize something. As the motor runs over its normal life cycle, it tends to work just fine with normal maintenance. But near the end of its system life cycle, we need to tighten up the maintenance processes and so on, because we recognize that the motor is near its design life. So the key point to understand about life cycle management is that the safety system needs to adapt to where they are in the life cycle. Now, this also applies to humans. A new hire on the job presents different hazards they would when they're a few weeks away from retirement. So, of course, the process of supervising new people versus older, near retirement age people also has to adapt to the life cycle of the system as well as their knowledge base and work practices, etc. So life cycle management is important to understand from the risk assessment process because we must integrate the idea of where the process is in its system life cycle when we assess its level of risk. Now, the second point suggests that safety is a line management responsibility. And line management means they have direct authority to direct the work. So there's no getting around this in the safety process, that safety is a top-down methodology. Safety has to be managed like any other process within the management system. So safety begins with the executive branch of the company, and it's driven or managed all the way down the organization through the frontline personnel. The idea that safety is productive is also important. Namely, it is possible to quantify the effectiveness of the safety system from the financial perspective, and it is possible to spend too much on safety. So it's important for all the managers to know, in listening to this presentation, that the idea that we can quantify how much money we should be spending on the safety process and pretty precisely calculate the effectiveness of that process is something that's possible. So management can manage safety like anything else. There are key indicators and cost values that we can measure, and we can determine if it makes sense to do what we're doing in the safety process. And then finally, the idea that safety requires upstream effort is also important, meaning that the further toward the design phase of the process you are, the cheaper and more efficient it is to make changes to that system. So engineering out a hazard when it's in the concept stage, in other words, it's in the mind of an engineer designing a process, is far less expensive and more effective than it would be to try and retrofit the same system after it's been installed and we've discovered that something is malfunctioning. So let's go to the next slide. Now, the concept that you see depicted in this slide is a concept that many organizations are already familiar with. But this is a matrix called a risk assessment code. And it actually identifies the idea that risk is actually a function of the product of two things. One is hazard severity and one is hazard probability. Now, hazard severity will be defined as the worst credible outcome that could happen from the energy source being evaluated. And probability is associated with the number of negative system outcomes over the system life cycle. Now, as you can see, the matrix indicates that there is an intersection between these two concepts. And management gets to decide what the organization is going to do based on the level of risk they're willing to accept. For example, you can see that there's under severity, catastrophic hazard severity, meaning very bad outcomes, and very frequent probability would constitute a category 1, and according to the legend, that would be an unacceptable risk, meaning that it's simply too dangerous. We have to do something about that. At the other end of the spectrum, when the severity would be negligible and the probability would be remote, that would be categorized as a level 4, which in this matrix is considered acceptable risk without intervention. The key point to get from this slide is that management gets to decide what numbers go in these boxes. In other words, how much risk are they willing to accept without intervention, all the way up to what they consider unacceptable risks that are going to need some sort of intervention. So it is critically important that this code be assessed with management decisions integrated into it, because it's going to drive the hazard assessment process later on. Let's go to the next slide. Now, it is important to keep in mind that the more specificity or more precision that we can bring to the definition process of severity and probability, the more scientifically accurate the hazard analysis becomes. So in this case, and by the way, these are just examples, this is not a suggestion that you should adopt these for your own company. The severity is defined in this situation as in terms of loss, severity of injury, the impact on the system, a financial indicator, and in this case, an incident energy value. So you can see how they've defined catastrophic to negligible in terms of the level of injury and so on. Probability is defined as the number of negative outcomes per a given number of iterations of use. So for example, resetting a circuit breaker, for example, the number of times that we would reset a circuit breaker and it would have a negative outcome, meaning the breaker would fail or cause an arc flash event. We would want to track that in terms of the number of negative outcomes per iteration. And we would integrate this concept into the risk assessment code process. So the key point to take from this slide is precision is good, is important, and that the more definition you can bring to the process, the more accurate the analysis will become. Let's go to the next slide. Let's talk a little bit about the human factors and how the human machine fits into this, because by far the human is the most unpredictable element in the safety process. And you know, the joke below about controlling human behavior is proof that herding cats is not so hard after all. It's kind of funny, but not totally, because getting people to follow safety procedures is very difficult, and that's the reason that violation of safety rules is so frequently a problem or a contributing factor to the accidents that happen on the job. So let's go to the next slide. So the basic problem is when we're talking about a piece of equipment, there's some kind of a stimulus, and then there's usually a response. And the response with hardware tends to be replicated pretty consistently. Not so with humans. There's a stimulus and then there's a mediation part of it where the human makes decisions in the middle and then they respond. And that's where the miracle happens, isn't it? That's where we get the variation in behavior. So in the safety profession, you'll see that we tend to try and engineer out the human process whenever we can, because we simply just can't control human behavior very well. So with that said, the idea of engineering controls is saying we're going to take the human element out of it when we're able. And if we are going to rely on people, then we're going to have redundant rules to make sure that the system is inherently safe. So let's go to the next slide. So what you see in front of you is a human error rate table. Now, we're not going to go through each one of these, but you can tell that the various types of tasks have failure rates associated with them from the behavioral standpoint. So, for example, the chance of a crew reacting during a disaster without having thoughtless or mindless reactions, the probability of that happening is 1 in 10. Going all the way to, say, 1 in 10,000, two qualified workers working off a written procedure has a human error rate of 1 in 10,000 iterations. And the credibility limit is considered 1 in 100,000 iterations, meaning when talking about humans, it is unreasonable to think that we could ever control behavior more definitively than that. The key point I want you to take from this slide is that human behavior has been quantified and measured. We know failure rates for many typical tasks, and these failure rates would then be integrated into the hazard probability part of the RAC that we talked about earlier, the Risk Assessment Code. And there's also a program called the Technique of Human Error Rate Prediction, which is called THERP. So just for background knowledge, it is possible to even measure human behavior failure rates, and this will help you to integrate this into your safety or your risk assessment code probability rates. Let's go to the next slide. Now let's talk about a few hazard analysis techniques that might be helpful to discuss, and then we'll just round out the story with some other ones that you can look into on your own. The first three we're going to talk about briefly here in this presentation, and then we'll, as I said, we'll allude to the other ones later on. The first concept is called critical grids, which is actually not normally a formal hazard analysis tool, but it is a way to sift or filter, if you will, the types of tasks that you do on the job and decide which ones to evaluate first. And I'll illustrate a critical grid in a simple concept like you would use if you were going to use one to buy a new car. We'll talk about job safety analysis that we all understand, but we're going to integrate risk assessment codes into them. Now, several of our customers are already doing this, but we want to give you a simple example of how this could add horsepower to your job safety analysis or your job hazard analysis process. Finally, I want to introduce a concept called MORT, which is called the Management Oversight and Risk Tree Analysis. Now, that discussion will primarily be important for safety people, but also for managers who can implement this in their own safety departments. Critically important hazard analysis tool and adds a lot of horsepower to the evaluation process. It also serves as a great accident investigation tool. We're also going to talk about some other types of analysis called failure modes and effects, which is a concept that determines how the system might fail and how it could impact other parts of the system. Events and causal factors analysis means it quantifies given events in the process and what it actually precipitates downstream from that event. Energy trace and barrier analysis evaluates how energy flows through our system and what ways barriers we have to control that energy. And then finally, change analysis is important when we talk about when the system has had a change. For example, when something trips out and it hadn't been tripping out before that, how do we evaluate the change? What changed in the process that caused the negative event to occur? So it's critically important to use the right tool for the right job. There are some 13 types of hazard analysis. These are only a snippet of that. And I want you all to know this so that you can explore this further if you would like. Let's go to the next slide. Here we have an example of a critical grid. And in this example, just to make it simple for anyone to look at, we're going to compare if we were going to buy 3 different vehicles and the evaluation criteria we would use to assess how those vehicles stack up against each other. So for example, in this case, on the y-axis, we'll list the types of vehicles we're thinking of buying. And on the x-axis, we'll list the evaluation criteria. So for example, the initial purchase price, the insurance costs, how fun it is to drive, fuel economy, and so on would all be listed on the x-axis. Now what we're going to do is evaluate them and we're going to rank order them. In this case, we're looking at 3 vehicles, a Jeep Cherokee, an Audi A6, and a Chevy Impala. By the evaluation criteria, we're going to rank order them, and 1 being the best at that category and 3 being the worst at that category. And we're going to evaluate that all the way across and then sum the numbers in the right column. So for example, with respect to the initial purchase price, the Chevy Impala is the cheapest vehicle, which would be the best price. The Jeep Cherokee would be the next best price, and the Audi would be the most expensive. We will do this across each one for insurance costs, fuel economy, resale value, and so on. And in the column on the right, the lowest point value would actually be the best option. In other words, that one got the lowest total number of points. So in this particular case, it was close, but the Audi A6, based on the person evaluating this, would be the best choice. The Chevy Impala would be the second choice, and the Jeep Cherokee would be the last choice in this example. Now, of course, there's no suggestion here that this actually is relevant to these vehicles. This is just to illustrate how to use the critical grid. But what you would do is on the y-axis, you would list the processes that you want to rank order. On the x-axis, you would list the evaluation criteria, which could include loss history, severity of injuries, impact on the system, loaded cost of accidents, so on. They would be all the evaluative criteria, and you could use something like this to decide which is the low-hanging fruit in your organization that needs to be evaluated first. So let's go to the next slide. Now, if we take a regular job safety analysis form and we add risk assessment to it, this would be something that we could use that would add power to the process. Now, this process is shown here as though it were, and it's oversimplified. We've broadly oversimplified this, but the task that we're going to be doing and evaluating is replacing a high voltage motor, a 2300 volt motor in an industrial facility. Now, I picked this one because it requires something like protective grounding to do it. So it's just meant to illustrate a point. So let's just look at a first couple of lines and see how it works. Initially, the job safety analysis in the left column lists the steps of the process, the actual tasks of each step. Then we're going to identify the hazards that include not only the type of energy, but the severity of each of those hazards. So for example, with regard to system shutdown or voltage testing, the severity rates would be more than 40 calories of incident energy and a 2300 volt shock hazard. The column after that is how are we currently, the typical or normal controls to manage that process. So with regard to the system shutdown, we would be using a written switching procedure, rubber gloves, and arc-rated clothing. Now the uncontrolled rack, or the rack that we're using our normal process, in this case would be considered a 3. Now this is based on the rack table that you had seen earlier. So in this case, a 1 or a 2 is bad, a 3 or a 4 is good. So in this case, it would be a 3, and we ask ourselves one more time, is there a need to do additional hazard controls? And in this case, using a chicken switch or a remotely actuated switch would improve the situation from a rack of 3 to a rack of 4. So in the far right column, we want to have all 3s and 4s if we're possible, using the scaling system that we currently have. Now you can see that the voltage testing and installing of protective grounds initially had a rack of 2, which we considered we needed to do something at that point. So we listed some additional interventions we would have to lower the rack from a 2 to a 3 in this case. So in the right column, we have all the numbers that are indicating the controlled rack of the process, and we want those all to be acceptable levels of risk per management. Now again, the difference between companies that are good at safety and great at safety are that column on the right. They're the ones who actually have identified that we've managed the risk rather than just we hope that we managed it well. Let's go to the next slide. I'd like to talk to you now about the Management Oversight and Risk Tree, which is also known as the MORT chart. Now I've got listed underneath, the subtitle is How to Become the Consummate Safety Consultant, partly because I've actually used the MORT chart myself in my career as a safety professional. Organizations that have sometimes hired us to do a system-wide or kind of a wall-to-wall evaluation of their safety process and also their management system as well would benefit from using the MORT chart to evaluate that system. If you can integrate the concepts included in MORT into your own safety process and your management system both, you will have a best-in-class process, no question about it. So I want you to understand how to use the MORT chart because it can be an incredibly valuable skill or tool to use. Let's go to the next slide. So the basics of MORT is that basically the Management Oversight and Risk Tree is a picture of the safety system. Properly applied, the MORT chart includes some 1,500 items to it. So needless to say, it is a very complete version of the safety process. Now the MORT chart would be used anytime you're doing, as I said, a system design where you're trying to build a best-in-class safety system, or if you've had a fatality and you want to do a complete systems review of what happened in that accident. The MORT chart is actually set up as a fault tree. That is to say, it has Boolean logic gates, which I'll explain in a moment. and it actually allows you to measure actually the flow of what happened in an accident. So it's actually set up as an accident investigation tool. But with that said, it also can be easily used as a planning tool, and I'll explain that in just a slide as well. One of the best values of the MORT chart is that it actually connects base level events with the actual accident itself. So for example, how did a person's behavior when they're just setting the job up or during the job briefing discussion contribute to the accident itself that happened, many processes later? The MORT chart allows you to do that. There's also something known as a mini MORT chart, which is an abbreviated version of this, which can be used for accident investigations of a lesser severity range. And there's also a MORT user's manual. And by the way, the MORT chart is a federal document. It was produced, well, initially in 1970, but it's been reproduced in the one I'm showing you here in the year 2002. And again, all of this documentation is available for no additional charge other than the taxes we've all paid on it. So the MORT chart user's manual will walk you through how to use this. And I will volunteer to any of you who are interested in doing the MORT analysis yourself. I will be happy to consult with you over the phone for no charge to help you implement this. If you're willing to put MORT into your organization and try to use it, I'm willing to help you try and use it well. So just consider that a free service from Grace Engineering to you. Let's go ahead and go to the next slide. Okay, let's take a look at the MORT chart and see if we can make some sense of what this chart can tell us. At the top of the chart is an injury or damage. This is known as the initiating event. And as I said, with a MORT chart, you're typically only doing this level of analysis if you've had a fatality, a catastrophic system failure, loss like an explosion in the facility, or you're trying to plan a best-in-class safety system if you're going to set up your safety system using this as a guide. So underneath that injury or damage box, you see one of the logic gates, which is called an OR gate. And the way to read an OR gate is whatever the event is above it, the box above it, everything underneath it, either this or that or both, could have occurred. So it's this or that. Not all of them necessarily will do it. So the way to read that chart is if I've had a loss or an injury, I've either had an oversight or omission, which is government speak for some part of my system didn't work, or I've assumed too much risk. Some of the customers that we have live in almost 100% assume risk, meaning they don't have much of a safety process. Most of what they do, they just try to do the best they can, but they haven't really formalized their safety process very much. So that's assuming risk. So it's kind of a legal reality that whatever risk you don't manage on behalf of management, you're assuming that risk. So let's continue reading the chart. The next logic gate you see underneath oversights and omissions is called the Boolean AND gate. Now the way to read an AND gate is the event that's above it, in this case an oversight or omission. Everything underneath that all had to occur at the same time. So the way to read this is if we've had an oversight or omission, we've had a specific control factor fail, and we've had a management system fail. And that abbreviation LTA is just government speak for less than adequate, meaning it's ineffective. So let's take a look at the chart and read it from top to bottom and see what we can make out of this. If we've had a loss or an injury in the system, we've either had an oversight or omission, or we assume too much risk, meaning we assume risk that we should have done something about. If we've had an oversight or omission, then we had to have a specific control factor fail and a management system fail. Now, the chart actually splits in two here, and the words that you have right next to that are sometimes written on the MORT chart, namely the what happened in an accident. If you want to know what system components failed that contributed to the accident, look at the left side of the chart, and we'll be looking at specific control factors. If you want to know why the accident happened, it will be a management system issue. So we would look at the right side of the chart. So there's a couple things we can take from this. Number one is every accident will have at least two causal factors. There will be a what happened and a why it happened. And the other thing that you need to know about this chart is if you want to make it into a planning tool, you reverse all the logic gates. That OR gate that you see at the top of the chart becomes an AND gate, and the AND gate becomes an OR gate. If you do that, you've converted this from what we call a fault tree to a positive tree, and you would use the positive tree when designing your own safety system. So hopefully that's helpful to get a flavor for it. We will give you a handout along with this presentation slides, just a picture of the MORT chart so you can see what it looks like, and you'll be able to get actual copies of the MORT chart online if you'd like. Let's go to the next slide. System safety techniques are by far the most effective means of controlling and measuring hazards, so let's use those. System safety takes a lot of the subjectivity out of working with management. It'll allow you to quantify things with hard data, things that typically people think can only be done altruistically, can actually be done with data objectively. It will take some effort to learn how to use these tools, no question about that, especially the MORT chart. With that said, it's well worth it. It'll give you capabilities that you never realized, both individually and as an organization. And don't do this alone. There are people like myself and others who have specialty training in these areas. We're happy to help you, and in my case, I'm willing to help you, as I said, on a phone call for no charge. So with that said, I'll turn it over to Banu, who's going to talk to you about some of the GRACE issues, and I certainly appreciate your time. God bless.
Thanks, John, again for the great information and the overview on the risk assessment, RAC codes, and also the applications. Also giving a lot of detailed information on the MORT charts. By the way, my name is Banu Srila, and I'm the Director of Product Marketing here at GRACE. My background is electrical engineering. I have about 20 plus years of experience in the power generation and distribution industry. And also I'm recently a certified electrical safety compliance professional as well. So I'm going to cover some of the topics that's relevant to the risk control as it's applied to one of the most commonly performed tasks of absence of voltage testing in the process of creating electrically safe work condition. So some of the topics I'm going to touch are going to be risk management 6-step process, risk as it's defined in 70E context, and also the risk management and the OSHA connection, hierarchy of risk controls, one of my most favorite topics, and the reason for using those hierarchy controls and their limitations, as we see in the 70E, and what some of the safety by design considerations that you should use for mitigating those risks. And last but not least, how GRACE can help you guys in reducing some of your electrical safety risks. With that, we'll go to the next slide. This slide shows the risk management process. Risk management, again, shares the 6 management system process elements. This is discussed in the Occupational Health and Safety Management Systems in their Annex P. So this has basically the leadership, policy, and then the PDCA cycle, as I'm showing in the slide. So the first and foremost thing, for any safety program to be effective, we have to have a full approval from the leadership. So leadership has to provide the complete buy-in in the system for it to be effective. And the second comes the policy. So the policy will define the vision of that program, the outcomes, and how to attain these goals as well. So then the PDCA cycle, which is a plan, do, check, and act, which is basically more like an iterative process. So planning has to be developed with goals in mind. So when you define those goals, you need to consider how to achieve these goals as well. Also, plan should have the elements from the previous audits or the training of the employees and also the previous incidents, and all these things has to come into the play. So when I go to the do, which is how the plan is being executed. So this is where exactly how this plan definition is going to be put in application or practice. So then the next one is the check. The check cycle basically gives the continuous monitoring of how this plan is being executed. And the last one here is the act within this, which is mostly measuring how the performance against the set of goals. So when I say the performance, how do you measure the performance of the outcomes, and how do you basically tweak them as you make this iterative? So please do understand risk management is an iterative process and it promotes continuous improvement. Risk assessment fits, as you see in the slides, plan and do cycle phases of the PDCA, and make sure to use the workplace instructions, incident reports, audits, training records to go into the planning phase as you define this risk management process. And as you do or execute this, it is an ongoing activity, meaning that we need to constantly evaluate the assessment is still valid. So I can give a great example. You do the risk assessment as part of the job planning process, and while doing or performing the job, you might notice something on the fly that might introduce additional exposure. So in that case, the qualified person should be capable of evaluating that risk and be able to put a mitigation in place as well. So understand it's iterative, and it's required to basically constantly monitor. Let's go to the next slide. Well, this slide provides the risk in terms of NFPA 70E context. So it's a basic risk definition as outlined in 70E. It's a combination of the likelihood of occurrence of injury or damage to health and the severity of the injury or damage to health that results from a hazard. This is what exactly 70E defines as risk. So for any risk, we need to estimate both the likelihood and severity. So John explained this pretty much in a great detail using the RAC codes and how to apply them using the matrices. So risk assessment has to include two components. One is the shock hazard. The other one is the arc flash hazard. For shock hazard, you need to understand the voltage, the boundary conditions, the personnel and other PPE required to protect the qualified and unqualified persons both against the hazards, and also the shock protection boundaries identified to include both the limited and restrictive approach boundaries. So if you want to take a reference from 130.4D table, which gives the shock protection approach boundaries for both the limited and restricted approach boundaries for both AC and DC systems. So the next one is the arc flash assessment. So when you look at the arc flash assessment, you need to understand the arc flash hazard likelihood and the severity, and you need to also understand the arc flash boundary conditions, which John again mentioned, the distance at which the incident energy equals to 1.2 cals per centimeter square or 5 joules per centimeter square. So arc flash PPE has to be used in accordance with 130.5G or 130.7C15. So there are the two labels which you can use. One is the incident energy calculation method, or the other one is the PPE category method. So just make sure that you can't use both on the same piece of equipment. You need to use either or. So and also make sure that you use the additional protective measures that needs to be used while doing the arc flash assessment as well. So the table 130.5 will give a good summary of how to estimate the likelihood and occurrence of the arc flash incidents as well. So qualification of the person performing the task and the equipment condition. So when you look at the criticality, these two are very, very important. So whenever you do the arc flash assessment, make sure that the person's qualification is taken into consideration, and also the condition of the equipment, because these two things play a significant role while someone is working near that equipment or on that equipment. So the last one I'm referring here is the documentation. The results of both the arc flash and shock risk assessments shall be documented. So it is very important that you document both the risk assessments on shock hazard and arc flash hazard. So the one small point I would like to bring to your attention, shock hazard boundary and arc flash boundary, those two things are independent. So sometimes arc flash boundary is farther than your shock boundary. So just make sure that you keep the note of it. So next, go to the next slide. This chart shows the risk management process, and it's adapted from the ISO 31000 standards. So this is specifically about what is the occupational health and safety's objective in the risk management. So OHS objective is pretty simple. It's freedom from harm. So how do we avoid the injury or damage to the health? So I would like to bring a quick correlation between NFPA and OSHA. So NFPA 70E basically sets the minimum consensus requirements for electrical safety work procedures, and it establishes the minimum standard for care. So on the other side, OSHA's electrical safety standards are performance-based. So OSHA validates basically how this freedom from harm is achieved, and NFPA 70E basically provides how to. So it's more like prescription-based, and OSHA is performance-based. So in other words, NFPA 70E fleshes out or gives a clear definition on how the performance standards should be met by defining minimum standard industry practices. So I want you guys to know that OSHA is the law and NFPA is not. So it basically 70 outlines how to comply with OSHA's electrical safety requirements. So let's take a look at what this OSHA connection here. So if you look at the hazard identification, we need to find, list, and characterize the hazards. Hazards are basically the risks we are referring to in the 70E context. And then the risk analysis has to be performed. And then by understanding the source of the risk, the cause and consequences of the risk. So once we get these two things identified, then you figure out the likelihood and the severity and the estimate of the risk. So this is basically the process as we go through. That's part of the risk analysis. Once you determine the risk analysis and evaluate this, you need to understand if the acceptable risk is free from the harm with the type of the risk control used. So we'll go through the risk control types in the next slides. So, and also it's an iterative process. As I mentioned previously, the risk management is an iterative process. You need to make sure that if there is a further reduction risk is required at the stage or not. That's where exactly you need the support and the buy-in from the management that define basically this is acceptable to our scenario. And if you look on the right side of the chart, it says a monitor and review, and then goes back to the establishing the context. So basically, this risk assessment or the management process has to be reviewed on a regular basis for continuous improvements. Let's go to the next slide. Well, this slide shows the hierarchy of risk controls as defined in the NFPA 70E context. So I was recently at a ESW conference in Fort Worth, Texas. Just want to bring my observation. Most of the presentations and the discussions at the conference were around the topics of risk and the elements of risk control hierarchy, what you see here in this chart. So before we go deep into this chart, I would like to emphasize that human factors are recognized as one of the major leading causes for the injuries. And then human errors again varies with the task and the type of environment they work around. So basically, while considering the risk control hierarchy, you need to understand you put the controls in place that has a less human intervention. So meaning, if you look at this chart here, your focus should be always on the elimination, substitution, or engineering controls, the top three of this pyramid, which are the most effective methods for reducing the risk, because usually these elements are applied at the source of the possible injury, and these are less likely affected by the human error. And the bottom of this pyramid, or the awareness, administrative controls, and the last one is the personal protective equipment, or PPE. These are the least effective methods as defined by the 70E, and these reduce risk because they're not applied at the source. And most likely, these are affected by human error. So 70E again defines the elimination, which is the top of the pyramid. That should be your priority in risk reduction. So elimination is a complete removal of the hazard of risk, so it does not exist at any time. So basically, some examples for that include using a 24 volts DC system in the control circuits over 120 volts, where you can eliminate the shock hazard. So again, for substitution, normally we'll minimize the hazard rather than eliminate it. So some of the things are basically using a current limiting fuse over a non-current limiting fuse as a substitution example. And engineering controls, again, isolate the employee from the hazard. And some of the engineering controls are remote tracking, interlocks, both mechanical and electrical interlock, or any kind of a door-mounted devices for measuring or performing the absence of voltage testing. How do you minimize through design itself, right? So those are the engineering controls. And the awareness, again, any kinds of the signs, labels, warnings, and alarms, those things that will be given. But again, understand when you look at the awareness, again, it's going to be impacted by how the human error is coming into play. So basically how operator or a maintenance person is going to interpret that awareness, and the environmental conditions, again, is going to play a significant role in it. So the next one on the list is administrative controls. When administrative controls come into play, it's again more into the policies, procedures, training, where you have more and more a human error possibility. So again, the training needs, the training methods, the type of PPE, all come under the next layers. So the use of PPE, again, is the last line of the defense in this risk control hierarchy, as though the PPE will give the protection against the injury and the hazard, it is again dependent on the employee or the user donning the PPE for that matter. So again, a lot of user possible errors in awareness, administrative controls, and PPE as I show here. So, I mean, the key takeaway from this slide is, as the safety professionals or people who are working in the electrical safety situations, your goal must be always either through elimination, substitution, or using the engineering controls. And identify which is the most effective method to control the risk. So it could be a single or a combination of the control that you can use. So if the failure of one control can lead that the other control below will perform. So each method is considered less effective than the above method. So for example, awareness is considered less effective over engineering controls, and the PPE is considered less effective over administrative controls. So I'm not telling the PPE is not required. So PPE is only going to protect in the event of incident. Okay. So the last point I would like to highlight here is understand that the residual risk always exists. It is not going to be a zero risk or a risk-free, right? So when you choose to do a task after using any of these risk controls that's outlined in this risk pyramid, you're still going to be left with some residual risk. And acceptable level of that risk varies greatly by the organization, the perception of the people, and also by the level of safety culture an organization has. Let's go to the next slide. So let's take a look at what are some of the objectives of using risk controls. So primarily, you're trying to reduce the likelihood of the exposure or reduce the severity of the exposure and achieving an electrically safe work condition. So what some of those considerations needs to be? So here, this one lists some of the considerations as you design the equipment during the planning phase of your project. So you can think of remote monitoring devices for voltage, current, and energy parameters. So by this way, when you have this remote monitoring features built into your cabinet, you can keep the distance from the person who is getting close to the equipment to get these measurements from that, right? And having a disconnect by the equipment. Think about a disconnect provided by the equipment side gives the operator a close control of that switch that he can use for de-energizing the equipment. And some facilities use the visible blade disconnects, or some users also use the voltage indicators by the equipment. So when they're doing the mechanical lockout tagout, it makes it easy for them to visually verify that the equipment has been de-energized through the visibility of the voltage presence or through the blades within that disconnect switch. And high impedance protected finger safe components. So some of those things where you can do the absence of voltage test from outside the door with the use of finger safe components. So the operator don't need to go inside the cabinet and expose himself or herself to that high incident energy. Then the remote opening and closing of the circuit breakers. So where the person is not getting in the close proximity of the cabinet, where in the event of the fault, he'll be exposed to that arc flash. And the arc resistant equipment in the last one is an example, great way to reduce that severity of that incident by providing the vents above this arc resistant gear, so the exhaust gases or the blast that will vent out to the top of that housing itself. Let's go to the next slide. Let's take a look at some of the limitations of the risk controls that I've seen in the previous slides. So first and foremost thing, I want you to understand that controls are fallible. So basically, there are potential failure modes that exist with every type of control that you see in the risk control hierarchy. For example, let's take a look at the elimination. A component failure, a defective equipment, and improperly maintained equipment, some other things could lead to an incident, right? You can do the substitution, but the employee interaction, which you don't have a control, and sometimes the procurement decisions that people do in selecting the components can lead to that failures. And as far as the engineering controls, some of the examples include the protective system failure and production pressures and people taking the shortcuts in bypassing those engineering controls could be a great example. As far as the awareness is concerned, there could be a situation where there are too many warnings and signs and too many indications that's coming out from a cabinet, and people probably disregard some of those. And also be aware that the awareness can also be impacted by the ability of that person and also the environmental conditions as well. And also the understanding of the instructions comes into play too. If the operator does not understand the instructions that's been put on that equipment, then he will be not able to use the control properly. So administrative controls, here we're talking about the policies and procedures. Some of the classic examples are procedures that are not being kept current, and the drawings that are not updated, right? The single line diagrams in the drawings that are not updated to identify all the possible sources of electrical energy, and not following the procedures. So the employees, again, not following those procedures can lead to a failure of this administrative controls. And the PPE, the last one, it's selecting a wrong PPE could totally change the game, and also employees not donning the PPE are some of the examples. Also, I would like to point, sometimes people don't inspect the PPE before and after use. That could also lead to that. So the key takeaway from this slide is even the best people make mistakes, right? So we need to understand that these mistakes can happen at the design phase or implementation phase or during the use phase. Anywhere these mistakes could happen. So that's the reason there's this different layers of the hierarchy that's included in this risk control. Let's go to the next slide. Let's take a look at how can GRACE help you guys in reducing your electrical safety risks. The first and foremost thing I would like to highlight here is we have over 2 decades of experience in electrical safety. So as our owner and CEO, Phil Allen, says, we live and breathe electrical safety every day. And also we are the innovators of permanent electrical safety devices. More importantly, we also work with electrical safety professionals like John Kolak, who has presented before. And our goal is to ensure that we'll find you guys the right solution. Sometimes our products might not meet all your needs, but definitely we will guide you in the right direction. So what you're seeing in the slide is some of our products, what we do. Under GRACE ports, we have the programming devices, or we call it the programming ports, which is primarily used for programming PLCs and other control devices while the doors are closed. And the next thing is our GRACE PESDs, which is permanent electrical safety devices. These are primarily used in mechanical and electrical lockout tagout. The voltage indicators, what you see here, are primarily used in the mechanical lockout tagout process to verify the voltage presence. And here in the bottom, you can see the voltage indicator that has been mounted over a disconnect switch. This is basically to provide a voltage presence visual verification for an unqualified worker or an operator by the equipment who is just disconnecting the switch and verify the voltage is present or not. And next product you see here is a voltage test station, which is a combination of a voltage indicator and test points. As you see here, you can pretty much do the voltage absence test from outside the door using an adequately rated digital multimeter. So you can perform the absence of test that's required by Article 120.5 of NFPA 70E from outside the door without being exposed to the high incident energy behind the doors. And the last one you see here is the GRACESense, which is the hotspot monitor, which is primarily used to monitor the loose connections of electrical systems. So primarily, the loose connections lead to a temperature increase as the resistance increases, and which would potentially lead to an electrical arc flash hazard. So this device basically continuously monitors the temperature anomalies of the bus bars or any conductors inside before the failure occurs. With that, we go to the next slide. As explained in my previous slide, here is a quick snapshot of how GRACE products help you guys to minimize the risk of exposure to incident energy in creating an electrically safe work condition. With that, we will answer your questions. And again, if you have any further questions after the presentation about the product or the presentation itself, please feel free to reach out to me or John Kolak, and we'll be happy to assist you guys. Thank you so much for your time.